Hello, good morning. We are going to recapitulate the idea about the effect of noise on analog communication system. It is one of the very interesting topic to analyze the effect of noise on analog communication system. So, we will consider the effect of noise on the baseband system as it is work as a reference for to calculate the performance of other systems as well. And now very first question arises, what is the baseband system? Baseband system implies that the signal you are generating, you are transmitting the signal through the channel and you are receiving the signal. So you need not to worry about any type of modulation process. So eventually you are not providing any carrier signal to transfer the signal through the system. Now as far as this carrier implementation is concerned, what this carrier does, we had observed that in the baseband system, the signal which is generated, in generally we will observe that it is low pass in nature. So that is nothing but low pass signal. When we modulate it, in the theory of modulation, we observed that we convert this baseband signal to the band pass signal. Because if you observe, you are taking the frequency of message signal, let us say 0 to FM, and if you modulate it on the FC carrier, then the band you get is from minus FC minus FM plus FC to FC, then FC plus FM. So basically that was in the positive axis you are having this particular value. And if you observe what is the upper frequency, you will observe that it is FC plus FM, and what is the lower frequency, we will observe that it is FC minus FM. So eventually you are getting twice of FM as the bandwidth of the system. In the case of double sideband system signal analysis, we had studied that particular part. So what will the baseband system do? Baseband system does not involve any carrier signal, so there will be no frequency translation. So if you are transmitting the signal, let us say 0 to FM, you will receive the signal also in the frequency band 0 to FM. So that's why it is the baseband system. Now we are presuming the receiver consists only of an ideal low pass filter with bandwidth W. The bandwidth W implies that the message signal is available from 0 to W frequency, and you want to filter out this particular signal itself, so you need not to worry about the component of frequency greater than W, frequency component greater than W. So we design a filter which will be low pass filter in nature, and it will process the frequency right from 0 to W. So if you take a mathematical representation, you will have the ideal low pass filter having frequency response minus W2 plus W, and the signal will be processed through it. That is one particular consideration. Now second point, there is noise as well, so it is also passing through the system. How it will behave? Now we are taking the thermal noise as a fundamental noise, and we had studied that this thermal noise is white noise as well as Gaussian process. So this thermal noise behavior can be represented by Gaussian and white noise processes. Now what is this white noise process? White noise process implies that you are having power component right from minus infinity to plus infinity. So you are having very wide band frequency component or the power component available on the entire frequency range. That is white noise. And when you pass it through an ideal low pass filter, so obviously it will consider the only signal component or the noise component which is available from minus W to W. So it will give you a band which is available from minus W to W for the noise consideration. So we can calculate the power of the noise at the output, that is represented by PNO, the noise power at the output. Noise power at the output is given by N0 by 2 is nothing but the power spectral density. With respect to frequency, you are integrating it, and the range of integration is corresponding to the range of ideal low pass filter, that is minus W to W. So if you solve it, you will get N0W. So this is nothing but the noise power at the output of the system. Now, second point is, let the received power be PR. That is the power received at the output. Now, the baseband signal to noise ratio, it is nothing but the metric which compare the effective power of the signal and to the power of the noise. So we had calculated the noise power, we had calculated the received power. So their ratio gives us the signal to noise ratio. So that is nothing but signal power divided by noise power. For which system we are talking about? We are talking about baseband system. So signal power to noise power for the baseband can be given as signal to noise ratio. In the suffix it is B, that is this notation we had represented over here. So that is nothing but received power, that is PR, received signal power, and received noise power is N0W. So that is PR upon N0W will give you the signal to noise ratio for baseband system. So let us take one particular example. Here we are considering a baseband system with a bandwidth of 5 kHz and N0 by 2, that is the power spectral density term, that is 10 to the power minus 14 watt per hertz. Now the transmitted power is 1 kilowatt. So the channel attenuation is 10 to the power minus 12. So we have to find out the SNR. Now in order to find out the SNR, first of all we calculate the received signal power. This can be given as transmitted power into the attenuation. So transmitted power is 1 kilowatt, that is 10 to the power 3 watt. Attenuation is 10 to the power minus 12, that's why 10 to the power minus 12, it will give you 10 to the power minus 9 watts. And N0 into W. W is nothing but 5 kilohertz. So 5 into 1000, that is 5000 hertz multiplied by, because N0 by 2 is given as 10 to the power minus 14. So we can find out N0 is nothing but 2 into 10 to the power minus 14. So by this way we can calculate this particular problem. We can solve this particular problem in this fashion. In some references it can also be observed in terms of dB scale. So in order to find out the dB scale value, what we can do, whatever signal to noise ratio we obtain, take the log value of this signal to noise ratio, log value based on 10. So log value base 10 of the signal to noise ratio multiplied by 10 will give you the dB scale value of this particular output. So that is about the signal to noise ratio calculation at the baseband system level.